Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a concept of dimensionless numbers. So in our last lecture, we have discussed the type of forces which are acting on the moving fluids. So this dimensionless number also depending on the forces. So before going to start this one, I'll give a brief about the previous what we have discussed. So in our last lecture, we have discussed the type of forces. So in the type of forces, first one is we have discussed about the inertia force. First one, we have discussed about the inertia force. And the second one, we have discussed about the inertia force, then viscous force. Viscous force. And next, we have discussed about the gravity force. And we have discussed about the pressure force. Then we have discussed about the surface tension force, and the last we have discussed about the elastic force. So these are the forces are impacting on the fluid flows. So here in the dimensionless number also, actually what is dimensionless numbers? So dimensionless numbers actually are the numbers which are obtained by dividing the inertia force to the rest of the forces. Actually, inertia force, it is the ratio of, you can write, it is the ratio of inertia force to the other forces, to the rest of the force, or we can write other force. So what are the dimensionless numbers are there? I'll tell you. So as we can see, it is the ratio of one force to other force, so that it won't have any kind of dimensions. Okay, that's why it's called dimensionless numbers. So what are the different types of numbers are there? First one is Reynolds number. First one is Reynolds number. And next one is, you can write Froude number. Froude's number. And next is Euler's number. Total we are having 5 numbers are there. Euler's number. And next is Weber's number. And the last one is Mach's number. Last one is Mach's number. So these are the 5 different type of numbers are there. And we'll discuss one by one. As I told you that the ratio of inertia force to the rest of the force need to be considered for to identify these numbers. So these are the dimensionless numbers are there. Okay, so first one is the Reynolds number. So Reynolds number, actually it is the ratio of inertia force to the viscous force. So this Reynolds number already have discussed number of times, but still let me write here. So I'll divide into these parts so that we can complete in between this. Yeah. So first one, light here, Reynolds number. So Reynolds number is indicated by Re. Reynolds number is indicated by Re, and it is the ratio of, as I told you, it is the ratio of, you can write. See, inertia force will be everywhere. Inertia force will be in the numerator part. Inertia force, and remaining force will be in the denominator part. Inertia force by viscous force. So inertia force, how is to determine, or how is to mention? So inertia force, actually we have defined Fi, and viscous force we have defined it Fv. So now we need to find out what is Fi, inertia force. So inertia force we have discussed about that inertia force is nothing but mass into acceleration of the fluid flow. So mass also we can write rho into V, because we know the density equal to mass by volume. So mass equal to density into volume. And acceleration we can write, this is velocity per time. Okay, so again we can write this is rho into V. So V per t, this is volume, and this is velocity, don't confuse. So volume per time. So volume per time also we can write A into T, area into V, area into velocity. So we can write rho into A into V square, and in bracket we can write this is volume per time, or volume per second. Volume per second we can write area into this is velocity. So how it came? Now we know that velocity equal to distance per time. So here volume means what? Length, width, and breadth, suppose. So that is also one distance. So here you can write this is length, width, or breadth divided by time. So here if I consider this length by time, this is our velocity, and this is width and breadth will be taken as the area here. Okay, so that's why area into velocity. That's why I have written here rho into A into V square. That is our inertia force. Similarly, in the viscous force, we know that viscous force is marked as FV, and this is, we have defined that tau into area, shear stress into area. So if you have not seen the video of the number of forces which are acting on the fluid flows, once see that one, so that you'll get a clarity in that. So how we have discussed. So shear stress into area. So shear stress, we can write this is tau equal to, we know the formula, that is mu into du by dy. So this mu into du by dy we have discussed during the Newton's law of viscosity. So this is mu into du by dy into area. So here again we can write this is mu into du by dy. So this one also can be written. So this du by dy we can consider v by L. Okay, v by L. So mu into this is length and this is velocity. Okay, so this one also you can consider mu into v by L into area. So here we can write this is, let's consider du by dy equal to v by L. Okay, this is our velocity gradient, this is viscosity. So finally what we got, mu into v by L into area. Now what is our formula? Now we know that Reynolds number equal to, as per the formula we can write, what is the value? We can write inertia force, that is rho into A into V square, rho into A into V square, and divided by this is mu into du by dl, that is nothing but v by L into area. Okay, so these are the things we can write here. Now if you cancel this one, like area will be cancelled, and v will be cancelled here, and L will be go to the top, so that we can write here this is rho v L, rho v, one v will be cancelled here and one v will be there, L will be come to the numerator, rho v L by mu. So this one again we can write in terms of v into L, and mu by rho. Let's take this rho down, so that we can write mu by rho is nothing but mu by rho. Let's consider this one. So this one we can write like this, or we can write this is VL by nu, because we know that mu by rho equal to nu. This is kinematic viscosity. Okay, this is kinematic viscosity. Now this is about the Reynolds number. Similarly, other number also can be described like this. So before going to describe this all these numbers, just I'll give a hint about the why these numbers are required actually, or why we are going to study about these dimensionless numbers. So actually I'll give some application of this dimensionless numbers. Okay, so these numbers can be applied in many areas. I'll give a few example of that. Suppose CFD simulation we are doing, computational fluid dynamics simulation we are doing. In the simulation we need many conditions. Okay, we need the help of these dimensionless numbers to to fix or to identify or to to keep some values for the simulation, make it correctly, some numbers required identify the flow velocity or what is the flow conditions. So to check all these things, we need to apply these things in the simulation. For different kind of flow regimes will be there, or which model need to be selected, which models or which equations need to be selected for the simulation. We need this help of this dimensionless numbers. Suppose this is one example I told you, or if you're going for design some systems, any kind of system design you are doing, okay, system design. So what is the system design is there? Mostly when we are designing or any kind of construction part, or if you are optimizing some conditions. So like suppose pipeline is there, okay, pipeline. Before going to design the pipeline, we need to optimize a lot of things, and suppose to design any kind of heat exchangers, okay, and suppose in aerodynamics conditions. So many things are there in the application about these dimensionless numbers. So in that case, we need to consider all these dimensionless numbers, which will help us. Again, in the flow, as we are talking about the flow. So in the flow also, in the flow determining, or the flow determination, like what kind of flow it is, or which kind of flow is required for the systems. Suppose the flow maybe, we know that flow are different types are there, okay. Suppose the flow is laminar flow, or flow is turbulent flow or transition flow. So that also can be calculated from this numbers, as this Reynolds number, actually this is used for, I have told you that this is used for the closed surface flow or open surface flow, and this also will be used to identify whether the fluid flow is laminar or transition and turbulent. That depends based on the Reynolds number values, actually. Like these things already have discussed in our previous videos many times. Like based on the Reynolds number, we can define whether the flow is turbulent or laminar or transition based on the Reynolds number value. The value is 2000, inside 2000 means we can say this is a laminar flow, and that to be depends whether it is flowing through the closed pipe or open pipe. So that depends. So here what equation we got here, so that is here final. So we can write this one as rho VL by mu, or we can write VL by nu, okay. And sometimes we used to write, this is for the length, linear dimension case, but sometimes when the pipe will be given, closed pipe will be given, that means we need to consider the diameter. So in that case also, here let me write, in that case we can write this is RE equal to, we can write rho VD by mu, or we can write similarly VD by nu. Any one can be considered. So this is about the Reynolds number, okay. Now the second number is Froude number, okay. Froude number also used to call. The Froude number, actually we can denote by FE. So here few things, if you remember, so it will be very easy. So okay, one thing is first concept is like ratio of inertia force to the other forces. That means in the numerator always the inertia force will be there, in the denominator other forces will be there. First concept that is you need to remember. And second concept is, only for the Reynolds number there will be no square root, only inertia force by viscosity, and remaining numbers are there what we are going to discuss. So all the numbers we have the formula, like inertia force to the viscous force, or inertia force by the gravity force, square root of that. So remaining all the numbers you will get in the same way. Suppose in the Froude number, so what is the ratio, what is the definition we can say? The Froude number can define the square root of, so I'll write directly here, in the square root of, as I told you, first in the numerator always inertia force will be there, inertia force to the gravity force, Now see, inertia force already have discussed, already you have derived here, inertia force here, rho AV square, and now we need to find out what is gravity force. gravity force also we have discussed in our last lecture. So here I'll just derive that values. I'll put the value here, so you can easily understand. Now inertia force we have already calculated. So here I won't write the inertia force. I'll write the gravity force, Fg. So the force due to the gravity, actually the force due to the gravity, we can say this is mass into acceleration due to the gravity, acceleration due to the gravity g. So again in the place of mass, again we can write this is density into velocity, volume, because density equal to mass by volume, so you can write this, and into g, again this one we can write rho into volume, we can write in terms of L, this is LQ, and we can write this is G. So because volume equal to, we can write length into length into length, that means length with breadth, so that is LQ we can write here. So similarly again if you again expand this value, so we can write this is rho into L square into L into G. So actually here why I have written the L square, because I can write this one in terms of area. Okay, this one length into breadth suppose, so that one we can write area. So that means here we can write this is rho into A, area, into length into G. Okay, this is the gravity force. Now as per the definition, the Froude number is defined as the ratio of square root of inertia force to the gravity force, which is when the fluid is flowing. Okay, now again I can write this one like in terms of, let's put the value of this rho a v square and this rho a l g. So if you put the value rho a v square and divided by rho a l g, so rho a will be cancelled, only v square by, now let's write v square by here into L G, root over will be there. Now if you remove the root over, so we'll get v by root over of L G. Okay, so this is the Froude number formula. Okay, so similarly remaining things also will be can be calculated. So all are very, very simple actually. So the third one, what we have discussed, what we are going to discuss here, Euler's number. So Euler's number is, now see, first one, Reynolds number we have connected with this viscous force. Okay, Reynolds number connected with this viscous gravity force connected to the Froude number. So inertia force will be always in the numerator. And next we'll see the pressure force will be related to the Euler's number, and surface tension will be for the Euler number, and elastic force will be for the Mach number. So let's go to the third point. So third point, as I told you, we are going to discuss about the Euler's number. So Euler's number also you can write this is E U. So it again also it is as I told you previously, as if you see this way, so you can easily remember, like we can without remembering or without thinking anything, we can give the definition, like it is the ratio of inertia force to the which one, gravity force already completed, next is pressure force. So it is the ratio of inertia force to the pressure force, but we need to consider the square root. That is the second condition I told. So here we can write Euler's number equal to, always we need to consider the square root. So square root, here in the denominator we can write Fi, and here I need to write Fp. So Fi already we have calculated, so here only I'll calculate about the Fp. So Fp equal to what? A pressure force. So pressure force equal to what? Intensity of pressure into area. Intensity of pressure into area, because we know that pressure equal to force by area. So here the pressure force which is acting, so that is intensity of pressure into area, that need to be considered. Okay, and here P we can directly put the value there, because already values are there in that. So here what I'll do, inertia force I can write this is rho a v square and divided by this is P into A, intensity of pressure into area. Now area is cancelled here, and here we can write this is v square by, if I take this rho to the denominator, that means p by rho, and this is root over. So here we can write, because here root over is not there, just have taken to denominator. So v square, if you square root want to remove, then we can write this is v by root over of p by rho. This is another one for the Euler's number. So this will be actually helpful for the capillary movement. For the capillary movement or free surface flow, this Euler's number can be utilized. Sorry, in the Euler's number actually we can use for the cavitation, because while seeing the cavitations and water hammers, there it will be required. And similarly, this is our Euler number. Next is what? Weber's number. So Weber's number also, as per the definition, if you see, it is very, very simple. Again, this Weber's number I'll just indicate by the WE. So denotation also, or you can say that denotation for the number, or you can say how to identify that is very, very simple. Weber number WE, Euler number EU. So short form we can write like this. So Weber number also again we can write equal to, it is the square root of Fi. This is fixed, square root fixed, Fi fixed. The next force what we have discussed, that is surface tension force. So Fs. So Fi already have calculated, and Fs equal to Fs also in the last lecture we have calculated in our previous video where we discussed the number of forces which are acting on the fluid flow. There we have discussed. So surface tension is actually nothing but sigma into L. Sigma into L, the surface tension per unit length into length. So in the surface tension again, what we'll do, we'll just put the value of directly here. So because Fi already we have solved here, this is rho a v square. So put the value here. We can write Weber number equal to root over of rho a v square divided by sigma into L. So again we can write this is, yeah, area we can write what? Area we can write length into length or length into breadth. So that is L square we can write, and this is v square. Similarly here again sigma into L, let's keep it, and root over of this. Now again we can write this is, so L will be cancelled here, one L will be cancelled, so remaining will be rho L v square divided by sigma root over. Now again we can write this is Weber number equal to, now take these two terms, this rho into L to the denominator, so sigma by rho L. So we can write this is v square by sigma by rho L, and this is whole root over. Now if you remove the root over, then what will get? V by root over of sigma by rho L. Okay, this is Weber number. Similarly the last one is Mach's number. So Mach number here M, only M, or sometimes it should be given MA also. So Mach number we can define this. So how to define? Only see, our formula is fixed, condition is fixed. One is we need to consider the square root. Another one is inertia force will be in the numerator, and the denominator what? Other forces. So other forces, all forces are already used. So only we have the forces of, that is elastic force. So elastic force again we can write Fe. So we can say it is the ratio of the square root of the ratio of the inertia force to the elastic force when the fluid is in fluid condition. So this is about the Mach number. So again we need to find out the elastic force. So there also elastic force also we calculated, that is E into A. So we have already calculated this one in our previous lecture. Again just I'll show you that to how to identify that value, Mach number value. So this Mach number, why it is required again? So Mach number also is required to find out the when the suppose jets are moving, whether the jets are moving high velocity or low velocity or medium velocity. To find out that one, Mach number required, and there by that we can say we can identify whether it is a supersonic flow or subsonic flow and sonic flow. So to find out this jet speed, this is used. So as per this one, we can write this is Mach number equal to this one, inertia force by elastic force. And inertia force, already we know that rho ab square, this is fixed. So again, elastic force, let me write here, Fe equal to, we know that actually elastic force equal to elastic stress into area. So I can write here elastic stress. Actually, it was given E into area, we have written previously. So E into A is nothing but that is elastic stress. So this one again, these things also you can write in terms of like K into A. Any one things can be considered. So this K into A also can be written K into L square, because A is the length into width or breadth. So here the same thing I'll write here, K L square. K L square. Now K is what? Now K we can define, this is elastic stress. K is nothing but elastic stress. This one we can write E or K. Okay. Now just cancel this one. We can get M equal to, here let me write here the same thing, rho AB square by KL square. So again the A I'll write rho into L square into V square by KL square root over this. Now L square can be cancelled here. So again the same thing what I'll do here, V square divided by K by rho whole root square. Now again this one we can, if you want to remove the square root, then V will be normal, V, this is K by rho. So this is the formula. Now this K by rho actually, we need to consider, let me write here, K by rho, root over of K by rho, actually we can write this is C. C is nothing but the velocity of the sound in the fluid. Velocity of sound in the fluid. So again in the final part we can write M equal to V by C. So mostly everywhere you will see this is the formula for the Mach number. Velocity of the fluid flow to the velocity of sound in the fluid. This is Mach number. So by this we can calculate the different types of fluid flows. Okay. So as you have seen that what we have discussed here, the number of forces and the dimensionless numbers. So it's very simple concept. Only we need to remember these are forces: inertia force and viscous force, gravity force, and next is pressure force, surface tension force, elastic force. Along with that, as the 2 or 3 concepts we need to remember. As I told you, first one, this is the ratio of inertia force to the other forces. That means always in the numerator, see, in the numerator part, inertia force is fixed. You can write inertia force is fixed. Okay. And denominator part, whatever the forces you want to put, you can put. Like you can put the gravity force, you can put the pressure force, you can put the surface tension force, or you just put the value of elastic force E. So the numbers, the dimension numbers can be identified from this. As we are seeing the force by force, so there will be no dimension. Okay, that's why it is called dimensionless. So I hope you understand this theory part. Like, you know, this is not the theory, somehow a little bit derivations are there to find out this. Anyway, the applications, as I told you. Still, if you are having any kind of query and doubt regarding this, you can give a comment in the comment box. Thank you all.